The question is, how does the white dwarf have stability or equilibrium? Because it has no nuclear reaction, so there is no thermal pressure to be produced by the nuclear reaction. So there must be some pressure produced somewhere. The pressure that is effective in a white dwarf star is called electron degeneracy pressure. Let us understand what this electron degeneracy pressure is. First, of course, gravitation is only attractive. It cannot be repulsive. The other three forces, electromagnetic, strong force, and the weak force, can produce both attractive and repulsive forces. But electromagnetic, strong, and weak forces are not really important inside a star. Electromagnetic forces are not important because we have a neutral object, so there is no charged object here. The strong and the weak only work through the nuclear reaction mechanism. And since the nuclear reaction is no longer available there, they are not available to you. But what produces the pressure then? The pressure is produced by just quantum mechanics. How can quantum mechanics produce pressure? Quantum mechanics leads to an additional type of interaction, which is what is called the electron degeneracy pressure. This is related to something which you are familiar with, the Pauli principle, which you must have studied in chemistry and physics. It is a repulsive force between the electrons. Pauli principle says that you cannot put two electrons in one state of the atom because they repel each other. Exactly the same way, the repulsion in between the electrons is what really produces the pressure in the white dwarf. Now, not only is it true for electron, it is true for all particles, and all particles have half integral spins, whether it is electron or proton or neutron, they all have spin half. So any particle which has a half integral spin, it can be half or 3/2, but the particles we know in nature are spin half. So whenever you have a half spin particle, it will repel each other when you go to quantum mechanics. Not at the classical level, but when you go to quantum mechanics. Thus, proton and neutron, as well as electron, they all obey Pauli principle, and they all have this repulsion. And this repulsion is what produces the electron degeneracy pressure. Now, in nature, there are actually two types of particles. One is called the Fermi particle, other is called the Bose particle. Fermi is named after Enrico Fermi, who was an extremely famous physicist. Bose is named after Satyendranath Bose, who was an Indian who really gave the original idea of what is now called Bose-Einstein statistics. Now, entities in classical physics, like electrons, behave like billiard balls in classical physics, but they behave like waves when you go to quantum mechanics. And things like light, which appear like wave in classical physics, appear like particles or what called photons in quantum mechanics. So what we call particles in classical physics, which behave like waves, all have half integral spins and obey Fermi statistics. It is called Fermi-Dirac statistics or Fermi statistics. What is the characteristics of Fermi statistics? It obeys Pauli principle, or it repels each other. So the particles of classical physics obey Fermi statistics and repel each other when quantum mechanics is applied. Exactly the opposite is true for Bose particles, which are called bosons. The Fermi particles are called fermions, the Bose particles are called bosons. For bosons, they are like waves in classical physics. You know, light is a wave, it can interfere and diffract and so forth. But when you go to quantum mechanics, it behaves like particles or photons. Now, these particles which are quantum mechanical don't repel each other, but they attract each other. So fermions repel each other and follow the Pauli principle, but bosons attract each other. And you may have heard of Bose-Einstein condensates, which are huge attractions of these particles. At the moment, we are interested in the Pauli principle and the fermions. So the fermions, which are half integral, have this repulsion which produces the pressure, and this is the pressure that balances the gravitation in the white dwarf star. This was realized by Professor Fowler in Cambridge in 1928 or so, as soon as Fermi-Dirac statistics was recognized, and this aspect was used by Professor Chandrasekhar to calculate the mass limit that the white dwarf can have, because mathematically you can calculate what will be the repulsive pressure, and you can see when it will balance gravitation. And of course, we are not worried about waves here. So what Chandrasekhar did was to calculate the maximum mass possible. Stop here.